Next application is related to, well, falling objects. So remember that if there is a difference between the rate of outflow and the rate of inflow, we need to find that as well. So it's going to change. If it was 4, you're going to enter 4 and the rest of it. Example of a falling object with air resistance. Falling object with air resistance. First of all, since we're talking about falling object with air resistance, it means that we're going to use the Newton's second law of motion. Let us review this guy. So let the air resistance on a falling object is proportional to its velocity. Its velocity, which is denoted by V. If G is the gravitational constant, then for the downward force, let us denote it by F, on the object with mass M, we have the following. M is equal to, F is equal to M times A acceleration, dv dt. Then F or M, A, M dv dt can be written as mg minus kv. So this is what we have. We have a differential equation when we are dealing with the Newton's second law of the motion. Example says an object of mass m is dropped from a helicopter. Find the velocity as a function of time. So what's the meaning of that? It means that, hey, now that you have the Newton's second law of motion, solve this differential equation. How do we solve this differential equation? So we know that m dv dt is equal to mg minus kv. Remember that m is the mass, g is the gravitational constant, and k is the constant of proportionality. Well, how do we solve this differential equation? So first of all, note that m is a constant, g is a constant, k is a constant. Well, it means that I can write this in separable form. How? This is dv divided by mg minus kv equals to dt divided by m. You only have v here and here. Then t as free variable, independent variable doesn't have anything. The rest of these values are all constant. So it's a separable differential equation. Separable. What's the meaning of that? It means that I can take the integral of both sides and start solving this. So first of all, here you get negative 1 over k ln of absolute value of mg minus kv equals to 1 over m t plus c sub 1. Well, now let's check to see if you can isolate v on one side, because question says find the velocity v as a function of time t. So let's multiply everything by negative k. We get ln of absolute value of mg minus kv equals to negative k over m times t, negative k c sub 1. You can call this guy c sub 2. So far we have ln of absolute value of mg minus kv equals to negative k over m t plus c sub 2. Well, what else? Let me erase the right-hand side. I need more space here. So mg minus kv is equal to, well, e to power negative k over mt plus minus e to c sub 2. Call this guy, for example, c. mg minus kv is e to negative k over m times t times c. So k times v becomes mg minus c e to negative k over m t, and v becomes mg over k minus c over k e to negative k over m times t. Here you can write it as plus and negative c and call it, for example, a capital C this way. So v of t is equal to mg over k plus c over k. You can call this guy another constant as well, or you can just factor out 1 over k and write it outside parentheses, e to negative k over m times t. So we wrote velocity as a function of